Hello, this is Dr. Hanaa Assil, and this is the part 2 of our general review for paper 6. So, last time we stopped here and we need to talk about factors that affect the rate of a reaction. So, when we talk about increasing the rate of the reaction, one of the factors that we can change is temperature. So you should know that increase in temperature increases the rate of a reaction. Any reaction, you increase the temperature, the rate will increase. And this is because particles gain more kinetic energy, move faster, collide faster, and more of the molecules have energy higher than activation energy, so there are more effective collisions per minute. When we draw a graph for this, remember that if the reaction is slow, then the slope of the graph is less than the slope for a faster reaction. So when we have this kind of graph in which we're measuring the total amount of product versus time, then at a lower temperature, the graph is less steep. Another factor that we can change is pressure, but remember that you talk about pressure only if we're talking about gases. If we don't have gases, then this cannot apply. And you have to remember that if we're talking about rates of reaction, increasing the pressure always increases the rate of the reaction. So when we increase the pressure, that means that we're pressing the particles closer to each other, so there is more chance of collisions, so more collisions per minute. Please do not mention kinetic energy if we're not talking about temperature. The only time that we say particles have more kinetic energy is if we're talking about increasing temperature. But for pressure, when we increase the pressure, particles are closer to each other, so more collisions per minute, or you could say more frequent collisions. Surface area. Now, surface area means the particles on the surface. So if I have a big piece of magnesium, for example, only the particles on the surface are reacting. But if I crush the solid or cut it into smaller pieces, then all these particles of all these surfaces will react. So we see that crushing the solid increases the rate because the smaller particles or the powdered solid has larger surface area, so more particles collide at the same time. If we increase the concentration of one of the reactants, so for example using more concentrated acid, this would increase the rate because of course now we have more particles, so more collisions per minute. So more particles collide at the same time. A catalyst is a substance that increases the rate of a reaction without being changed. This is because the catalyst provides an alternative pathway for the reaction. This lowers the activation energy. Remember, we said the activation energy is the difference in energy between reactants and the intermediate, which is at the top. So whether we're talking about an exothermic reaction or endothermic reaction, what the catalyst does is it lowers the activation energy, and that is why it makes the reaction fast. If we're talking about enzymes, then remember that enzymes are biological catalysts and they are proteins. They speed up reactions in living cells, but the difference between enzymes and other catalysts is catalysts are not affected by temperature, so you can use the catalyst at a very high temperature, but enzymes, if you put it in temperatures higher than its optimum temperature, then of course you should know from biology that the enzymes will become denatured and they will no longer act as catalysts. How do we study the rate of a reaction? So if we have a reaction that's giving out a gas, then what we can do is measure the volume of gas every minute using a gas syringe. So you put the reaction mixture in a flask connected to a gas syringe, and you measure the volume of gas every minute. Now, any reaction at the beginning is fast. You have to know that when we add reactants at the beginning of any reaction, the reaction is fastest at the beginning, because at the beginning we have more particles colliding. But as the reaction proceeds, then the rate slows down, and in the end we have a rate of 0 or no more gas is coming out because the reactants are being used up, so less collisions. Please, when he says why do we have a flat area in the graph, or why did the reaction rate stop, then you have to look at the reactants, the one that is not in excess. So if he says one of them is excess, that's not the one we're talking about. The one that is not excess has been used up. So there is less collisions or no more collisions. So if I'm doing an experiment and I have graph A, and he says he did something to the experiment to make it slower, then my graph should be graph 1. If he did something to the experiment and it made it faster, then you have graph 2. So if he says draw the graph for the faster reaction, it is graph 2. But if he's saying we're using more reactants, then we get graph 3. So graph 2 is faster, graph 1 is slower. And graph 3 is faster but using more reactants. So what did we do, for example, in experiment 2 to make the reaction faster? We used higher temperature or higher concentration or higher pressure if we're talking about gases. Or we used a better catalyst, or we crushed the solid, so now we have larger surface area. In that case, you get graph 2 instead of graph 1 or graph A. Another method of following the rate would be to measure the change in mass. And this also is for an experiment that gives out a gas. So of course, if I put the reaction on a balance and it is giving out a gas, the gas escapes. That means that the mass will decrease. So if he says, why is the mass decreasing? Because a gas, whatever gas it is escaping. So if it's a metal with acid, then the gas is hydrogen. But if it is a carbonate with acid, then the gas is carbon dioxide. So in both cases, the mass decreases. Why? Because a gas escapes. Now, which one is faster, experiment 1 or experiment 2 in that graph? You should realize that if a reaction is faster, then it will lose mass faster. So experiment 2 is a faster reaction. What if we don't have a gas, we have a precipitate? So in that case, for example, this experiment is a very common experiment that he tells you that he did. Sodium thiosulfate with hydrochloric acid will give out sulfur precipitate, which is a yellow precipitate. So it forms a yellow solid. So I can use that to measure the rate. I add the two reactants and I start the timer and measure the time taken for that X below the flask to disappear. If we're looking through the solution, we can see the X that is written below the flask, but as the solution becomes cloudy, then at some point the X will disappear. So what I'm measuring is time taken for the X or for the cross to disappear. So I can repeat that, for example, at different temperatures. Remember that a faster reaction will take less time. So as we increase temperature, for example, we said the reaction should become faster, and that means the time taken for the cross to disappear will be less. In this question, he says an organic compound decomposes to give off nitrogen gas. The speed of this reaction can be determined by measuring the volume of nitrogen formed at regular intervals. Typical results are shown on the graph. So he drew the graph for you. The reaction is catalyzed by copper. Sketch the graph for the catalyzed reaction. We said if this is the graph for our original reaction, then he did something to make the reaction faster. Of course, if I add a catalyst, then the reaction is faster. And he's saying sketch the graph. Well, if it is faster, then the slope is steeper and it ends at the same final volume because I'm starting with the same amount of reactant. How does the speed of this reaction vary with time? Remember that we said this kind of curve means that at the beginning the reaction was very fast, and then the reaction rate decreases as time goes on. So at the beginning it was fast, and then it decreases until the rate becomes zero at the end. Why does the speed of the reaction vary? We said for any reaction at the beginning the reaction is fast, but then it slows down. Why does it slow down? Because the particles of reactants are being used up, so there is less collisions per minute. This is a question at the end of paper 6, and it says an aqueous solution of hydrogen peroxide decomposes very slowly to form oxygen. The speed of decomposition can be increased by using a catalyst. Two possible catalysts are the solids copper 2 oxide and chromium 3 oxide. Plan an investigation to find out what? Pay attention to what he's asking. He wants an investigation to find out what? He wants an investigation to find out which of these two oxides is the better catalyst. So I have two solids and I want to know which one is the better catalyst. What should we do? Well, we said if we use a catalyst for hydrogen peroxide, it gives off oxygen gas. So I can use that to measure the rate. So I can tell him to weigh a specific amount of the first catalyst. So let's say 5 grams of the first catalyst using a balance, put into a flask connected to a gas syringe, and then add a specific amount of hydrogen peroxide. So let's say 25 centimeter cubed of hydrogen peroxide to the flask through a dropping funnel. That's how we do it. And determine the volume of gas collected in a specific amount of time. So amount of gas collected in 2 minutes, for example. So I do this for the first catalyst, and then I tell him to repeat the same thing with the other catalyst. So repeat using the same what? Using the same mass of the catalyst, the same volume of hydrogen peroxide. I could also mention that it would all be at the same temperature, and the one that gives more gas in 2 minutes is the better catalyst. Are we following how to explain all of these? Okay, another question says, this is similar, but it's a little bit different. Hydrogen peroxide solution breaks down to form oxygen. This decomposition is if a catalyst is not used. Plan an investigation to show that copper 2 oxide is a suitable catalyst for this reaction. You can use aqueous hydrogen peroxide, common laboratory apparatus, and he's specifying that he wants you to show that copper oxide catalyzes the reaction. It catalyzes the decomposition of hydrogen peroxide, measure the rate of the reaction, show that the copper 2 oxide is unchanged at the end of the decomposition. Remember that we said definition of catalyst is a substance that speeds up the reaction without being changed. So if I start with a certain mass of the catalyst at the beginning, I should end up with the same mass at the end. So what should I explain? Basically the same thing, but let's go through this. He says put a certain volume, so I like to specify 25 centimeter cubed of H2O2 into a flask connected to a gas syringe. So we're using the same apparatus, a flask connected to a gas syringe. Measure the volume of gas collected in 1 minute. So remember that this is the reaction with no catalyst. So I'm going to do it first with no catalyst. Measure the volume of gas collected in 1 minute. And then I'm going to weigh a certain amount of copper oxide using a balance. So here I say weigh 5 grams. It doesn't make a difference what it is, but just specify, of copper oxide using a balance. Put into a flask connected to a gas syringe. Add the same amount of H2O2 that we used at the beginning using a dropping funnel. Measure the volume of gas collected in 1 minute. The gas collected with copper oxide should be much larger. to indicate that the copper oxide is a catalyst. So if the copper oxide is a catalyst, then the amount of gas collected in 1 minute should be much larger. Okay, and then he says, show that copper oxide is unchanged. Well, what do? The copper oxide is a solid inside the solution. So filter the solution containing the copper oxide, wash the residue with a few drops of distilled water. Of course, the residue is the copper oxide. Dry between filter papers, weigh the residue. Remember, we added at the beginning how much copper oxide? We added 5. If it's a catalyst, then at the end, I should also end up with 5 grams, indicating that the copper oxide was a catalyst and it remained unchanged. What if we have 2 types of fuel and I want to compare the energy value of the fuel? So sometimes he says I have methanol and ethanol and I want to know which one is a better fuel. So what do? We measure a specific amount of water into a test tube using a measuring cylinder. So I'm putting in that test tube, for example, 25 centimeter cubed of water. It doesn't have to be exact, so I can use a measuring cylinder. Determine the initial temperature of the water. And then I'm going to weigh a specific amount of the first fuel. So let's say the first one was methanol. So I will say weigh 25 grams of the methanol in a spirit burner. Can you see that container? That container is called a spirit burner using a balance. Place the burner below the test tube, light it, allow it to heat the water for 5 minutes. Note the final temperature of the water. So I'm heating the water using the first fuel. And then I'm going to repeat using 25 grams of the other fuel, same volume of water, same time, 5 minutes. Determine the final temperature of the water. The fuel that causes a higher increase in temperature is the better fuel. So the one that will heat the water to a higher temperature in 5 minutes is the better fuel. Of course, this kind of experiment, the possible sources of error would be loss of heat to the surroundings and incomplete combustion of the fuel if the fuel did not burn properly. So the precautions that we should take, if he's asking about precautions to avoid these sources of error, we say insulate the experiment, or we say, we insulate the experiment to prevent loss of heat. I need to prevent loss of heat to the environment. So I can use, for example, a copper can instead of the test tube. Then this will help to heat the water fast. This is another question, fats and oils. Unsaturated fats and oils. Do you remember what we mean by unsaturated when talking about in organic chemistry? Unsaturated means it has 1 carbon-carbon double bond. These double bonds react with bromine water, which changes color from orange to colorless. Now, he wants you to plan an experiment to do what? To compare samples of oil. So he has sunflower oil, olive oil, and butter to find out which of these contains the largest number of carbon-carbon double bond. Of course, the more double bonds in the structure, the more bromine it will use. So what should we do? Well, put 10 centimeter cubed of the first kind of oil in a test tube. And then we need to add, he says you should add an organic solvent to dissolve the oil. So let's say we add 10 centimeter cubed of ethanol using a measuring cylinder to dissolve it. And then we start adding drops of bromine water using a dropper. Count the number of drops needed for the orange color to remain. Remember that bromine water that I'm adding is originally orange. Now, as I add it to the oil, it will react with the double bond and become colorless. And then I add some more and it becomes colorless. When all the double bonds in the oil have reacted, then the bromine water remains in the solution, so it remains orange color remains. Then Repeat, using the same amount of the other oils. And of course, the one that needs more drops of bromine is the one that has more carbon-carbon double bond. Okay, the next chapter that is very important is electrolysis. And you should know that electrolysis is the breakdown of an ionic compound, molten or in aqueous solution, by the passage of electricity. So we're going to have a liquid in that beaker that we call the electrolyte, and the electrolyte is molten or aqueous solution of an ionic compound, so it has positive and negative ions that are free to move. And then I'm going to put electrodes. The electrode is a rod that allows electric current to pass through, and we said these electrodes are usually made of graphite, or if we need a metal, we said we used an inert metal like platinum. And we put the electrolyte in the beaker. So this is the one that has positive and negative ions. Remember that the electrode connected to the positive end of the battery is the positive electrode, and it's referred to as anode, and it will attract the negative ions in the electrode. Now, the electrode connected to the negative end of the battery is the negative electrode, and it attracts the positive ions. Please note the flow of electrons in the wire. The electrons in the wire, of course, the wire is made of a metal, so it has delocalized electrons that are free to move. The electrons are attracted to the positive end of the battery and repelled by the negative end of the battery. And you know that the metals or hydrogen are the ones that form positive ions, so they are the ones that go to the cathode and react, while the non-metals are the ones that are negative ions, so they go to the anode and react. So for example, if he says he's doing electrolysis of molten sodium chloride, what ions do we have? This is how we think about it. We said the ions, molten sodium chloride means I have sodium ions and chloride ions. The sodium ion is positive, so it goes to the cathode. Chloride ion is negative, so it goes to the anode. So this forms chlorine gas at the anode and sodium metal at the cathode. And please note is the question asking, what is observed or what is the name of the product? So at the anode, what is observed is bubbles of green gas, but the name of the product is chlorine. And remember, it's chlorine, not chloride. The chloride reacts to form chlorine. Now, at the cathode, name the product, it's sodium. But what is observed, we see sodium. Of course, sodium is a metal, so we see it as a gray metal deposit or a silvery metal. What if we're doing molten lead 2 bromide? Molten means, again, heating until it melts. So I have molten lead 2 bromide and I'm heating it. Where are the ions? The ions are lead 2 plus and Br minus. The bromide ion goes to the anode. It forms bromine. So the name of the product is bromine. The observation is reddish brown fumes. The lead 2 plus ions goes to the cathode. It forms lead metal. So the observation is gray metal deposits. What if we're doing molten copper 2 chloride? Again, molten copper 2 chloride means I have copper 2 plus and the Cl minus. The Cl minus goes to the anode and forms chlorine. What I see or the observation is bubbles of green gas. Please give him what he wants. Is it observation or name of product? Because this is the main mistake everyone does. Copper 2 plus goes to the cathode. So if we say name the product at the cathode, it's copper. If we say what is observed, it's reddish brown metal. Okay, what if we're doing aqueous solutions? Electrolysis of aqueous solutions. Aqueous means I have water. So if we say we're doing electrolysis of concentrated HCl, that means I have hydrogen ions and chloride ions from the HCl, but I also have the ions from water. Water ionizes to form H plus and OH minus. Now at each electrode I have a choice and we have to choose one substance at each electrode to react. So at the anode here, I have either chloride or hydroxide will react. How do we decide? If we're deciding between chloride and hydroxide, the one present in larger amount is the one that reacts. We're deciding between what? Chloride and hydroxide. The one present in larger amount is the one that reacts. So if we say concentrated, means I have more of chloride, so it's the chloride that reacts to give chlorine, and I see bubbles of green gas. At the cathode here, my only choice is H plus ion, so it reacts to form hydrogen. So what I see is bubbles of colorless gas. What if I'm doing electrolysis of concentrated sodium chloride? Again, what are the ions that I have? I have Na plus and H plus and Cl minus and OH minus. So at the anode, again, which one is going to react? We said chloride and hydroxide, the one that is present in larger amount. This is concentrated, so I have a lot of chloride, so this is the one that reacts. On the other electrode, we have a choice between Na plus and H plus, and you have to remember, the one that is lower in the reactivity series is the one that reacts in electrolysis. So which one is lower in reactivity series? The H plus, it's the one that reacts, not the Na plus. So at the anode, the chloride reacts. At the cathode, the H plus reacts, and that means I'm left in solution with sodium hydroxide solution. I'm left with the Na plus and OH minus. What if I'm doing dilute sodium chloride? Then my ions are still the same, but now this is dilute, means I have a lot of hydroxide ions. When hydroxide ions react, they form oxygen gas. On the other end, I have a choice between Na plus and H plus. We said the H plus is the one that reacts. If I'm doing electrolysis of aqueous copper sulfate, so I have copper ions and sulfate ions, and I also have H plus and OH minus from the water. Which one is going to react at the anode? At the anode, I have a choice between sulfate and hydroxide. Please remember, when I have a choice between sulfate and hydroxide, it is the hydroxide that always reacts. Don't say which one is more. Which one is more is when we were comparing between chloride and hydroxide. But comparing between sulfate and hydroxide, it's the hydroxide that reacts to give oxygen gas. Now, if we're comparing between copper 2 plus and H plus, we said the one lower in the reactivity series is the one that reacts. Which one is lower in the reactivity series? It's the copper, that's the one that reacts. So copper ions react, hydroxide ions react, and I'm left in solution with H plus and sulfate ions. This is sulfuric acid. So remember that the blue color of copper sulfate solution disappears. Why? Because the copper ions react at the cathode, the hydroxide ions react at the anode, and I'm left in solution with sulfuric acid, which is a colorless solution. Dilute sulfuric acid, again, choice between sulfate and hydroxide, it's the hydroxide that reacts. The other end, I have only H plus ions, so that gives me bubbles of colorless gas. What is electroplating? Electroplating is the use of electrolysis to form a thin coat of metal on an object or ornament. So basically, it is covering a metal with another metal. Electroplating is covering a metal with another metal. Why would we do electroplating? Why am I covering a metal with another metal? This is usually to protect the object from corrosion, or to give it a nicer appearance or a more expensive value. Remember that when we do electroplating, the spoon should be clean. So the first thing I do is I should clean the surface of the object in order to allow the silver to stick to it properly. And during the electrolysis, the spoon should be rotated to be coated evenly. So how do we do electroplating? I put the spoon, connect it. I have to connect the spoon or the object I'm trying to cover to the negative end of the battery because I want the metal ion to go to the spoon and the metal ion is positive. So the spoon must be negative. Now, if I'm trying to cover it with silver, then the anode is silver. But if I'm trying to cover it with any other metal, then that's the metal I will use for the anode. So what I see is the anode will dissolve in solution and become smaller because the silver becomes Ag+. So that rod becomes smaller. Now the Ag+ will go to the spoon and cover it so that I get a gray silver metal depositing on the object that I'm trying to do electroplating. So this is how we explain electroplating. If he's saying explain how to do electroplating, connect a silver rod to the positive end of the battery. Of course, we're using copper wires for all of this. Clean the surface of the spoon with sandpaper. Usually he tells you, he gives you sandpaper and you have to use it. What do we use it for? To clean the surface of the spoon. Put the spoon in a beaker containing a solution of the metal that you're trying to cover. So I'm trying to cover the spoon with silver, then my solution is silver nitrate solution. Of course, we choose nitrates because all nitrates are soluble. Of course, if I'm trying to cover my spoon with chromium, then my anode is made of what? Of chromium metal. And my solution will be what? Chromium nitrate solution. And then we connect the spoon to the negative end of the battery, and that will cause electroplating. The next thing we need to know is reaction of metals. So you should know that all metals react with oxygen. So when you burn, for example, magnesium, magnesium burns with a bright flame. When it burns in oxygen, it forms magnesium oxide, and magnesium oxide is a white solid. So if he says observations when you burn magnesium in air, the magnesium burns with a bright flame and a white solid is formed, or we refer to it as white ash. This question says calcium burns in air to form calcium oxide. The reaction is vigorous and some of the calcium oxide can be lost as smoke, and we don't want that to happen. Plan an investigation to determine the maximum mass of oxygen that combines to form calcium oxide when 2 grams of calcium granules are burnt in air. So I'm going to burn 2 grams of calcium and I want to know how much oxygen is going to react with it. How do I know how much oxygen reacts with it? Well, we can weigh it at the beginning, weigh it at the end, and the difference will be the mass of oxygen, right? So what are we going to do? We're going to put a specific amount of calcium, put 2 grams of calcium into a crucible and lid, weigh using balance. So we're weighing the crucible and lid and calcium. Cover the crucible and heat it. Remove the cover several times to allow more air in. So one question is, why are we covering the crucible? Why don't we just leave it? Because he said the reaction is vigorous and we don't want to lose some of the calcium oxide. So why are we removing the cover several times? We remove the cover and then we put it back. Why? To allow more air in. So I want as much oxygen to react with the calcium as possible. Now, weigh the crucible. We're going to finish the first part, leave it to cool, weigh the crucible and lid and its contents. But how do I know if the reaction has finished? I have to reheat and reweigh several times until the mass is constant. So once the mass is no longer changing, of course, at the beginning, the mass should what? The mass should increase because calcium is reacting with oxygen to form calcium oxide. So the mass will start to increase. Once there is no more increase in mass, then the reaction has finished. So subtract the initial mass of crucible and lid and calcium from the final mass. That will give the mass of oxygen U. Then we have reaction with water, and we said some of the metals react with cold water and some react with steam. And you have to remember in the electrochemical series which ones react with water. The one that reacts with cold water is the more reactive metal, potassium, sodium, calcium. And when they react with cold water, they give the metal hydroxide. So potassium in water gives potassium hydroxide. Sodium in water gives sodium hydroxide. Plus what? Plus hydrogen gas. Now, all the other metals that are above hydrogen in the reactivity series will react with steam. So magnesium with water is very slow. So we react it with steam, but when the metal reacts with steam, it gives the metal oxide, magnesium oxide, aluminium oxide, zinc oxide, plus hydrogen gas. Anything below hydrogen in the electrochemical series will not react with water or with acid. So remember that copper and any other metal below copper in the electrochemical series or in the reactivity series does not react with water and does not react with acid. So sodium in cold water, you need to know the observations. You have to know that first of all it reacts with cold water, so it gives sodium hydroxide plus hydrogen. Now what do we observe? Sodium is in group 1. It floats, it darts, melts, or it disappears. We get vigorous fizzing since it's giving out hydrogen gas, and the bubbles of hydrogen gas may catch fire because hydrogen is flammable. Now, if I need another observation, remember it's forming sodium hydroxide solution that is alkaline. So if I should have litmus paper or I put universal indicator solution in the flask, then it will turn blue. Calcium also reacts with cold water, but calcium is in group 2. Calcium, when it reacts with cold water, again, it gives calcium hydroxide plus hydrogen, but now it does not float. It sinks. Calcium is in group 2. It sinks. You still have strong fizzing because it's still giving out hydrogen gas, and the solution becomes milky if I need another observation because the calcium hydroxide that is formed is not soluble in water. So the water starts to become milky. When magnesium reacts with steam, we said it gives magnesium oxide plus hydrogen. Now, if we're asking what do I see, the magnesium burns with bright flame. The magnesium oxide, you remember, is formed, it is a white solid, and we get hydrogen gas given off. Zinc again with steam gives zinc oxide plus hydrogen. Now, when we have metals reacting with dilute acids, the metals above hydrogen will react with acids. So this will give the salt plus hydrogen gas. Magnesium is very reactive, so it gives a lot of bubbles of hydrogen gas. Now, zinc is less reactive, so it gives less bubbles. Copper is below hydrogen in the reactivity series, so copper does not react with acid. Displacement reactions, the more reactive metal displaces the less reactive metal. So if I put zinc in copper sulfate solution, you have to know that copper sulfate solution is blue. But when it reacts, it forms zinc sulfate, and it reacts because the zinc is more reactive than copper. If I put a metal that is less reactive, then no reaction will happen. So zinc displaces the copper because it is more reactive, and that means the blue color of the copper sulfate solution becomes colorless. The piece of zinc that I added will dissolve, and I'm forming copper metal. You have to remember that the appearance of copper metal is a reddish brown or reddish precipitate or reddish solid is formed. So this experiment says plan an investigation to show the order of reactivity of 3 metals. So I have 3 metals and I want to know which one is more reactive. What should I do? I should react the same masses of each of them to the same volumes of dilute hydrochloric acid. What am I measuring? The volume of gas collected in, let's say, 1 minute. The one that gives more gas is the more reactive. So how do we explain that? Weigh 5 grams of the first metal using balance. Put into a conical flask connected to a gas syringe. Add a certain amount of dilute hydrochloric acid to the flask using a dropping funnel. Determine the volume of gas collected in 1 minute, and then you're going to repeat using the same mass of the other metals, same volume of HCl. The one that gives more gas in 1 minute is the one that is more reactive. This question says brass is a mixture of two metals, copper and zinc. Copper does not react with sulfuric acid. Zinc reacts with hot dilute sulfuric acid to form the soluble salt zinc sulfate. So that just tells you that the copper does not dissolve in sulfuric acid. The zinc will dissolve in hot dilute sulfuric acid. So plan an investigation to find the percentage by mass of zinc in a sample of brass. In your answer, you should include how to calculate the percentage by mass of zinc. So what should we do? We have brass, mixture of two metals. So the first thing you do is weigh a certain mass of the brass using a balance. Put into a beaker, add excess dilute sulfuric acid and heat, because he says the zinc will react with the hot dilute sulfuric acid. Copper does not react. So stir with a glass rod until no more solid dissolves, so you're sure that all the zinc has reacted. Filter through filter paper and funnel. The copper will be collected as residue. Wash the residue with a few drops of distilled water. Dry between filter papers. Weigh the residue, so that would be the mass of the copper. Now he is asking about zinc, so we're going to subtract from the initial mass to obtain mass of zinc, and of course the percentage of zinc will be the mass of the zinc over the total mass of brass times 100. This is another question. He says iron rusts when in contact with air and water. You are provided with iron nails and 3 different samples of water: tap water, seawater, distilled water. And he says plan an investigation to find out which sample of water causes iron to rust the fastest. So what are we going to do? Remember that in these kinds of questions, it's a good idea to draw. So what we're going to do is we're going to put the iron nails into equal volumes of tap water or distilled water or seawater. Leave them at the same temperature for the same time. But what are we going to measure? How do we know if one has rusted more than the other? Remember that when iron rusts, it reacts with air and water, so it changes into hydrated iron 3 oxide. That means its mass will increase. So the one that rusted more is the one that has increased in mass more. So what do? Weigh the iron nails first using balance. Put into different test tubes. Add a specific amount of one of the samples of water to each test tube. Leave at the same temperature. So you have to mention, for example, leave at room temperature for the same amount of time. Usually any experiment involving rusting, we leave for 5 days because rusting is a very slow process. Then at the end of the 5 days, what should we do? Remove the nails, put into separate beakers, dry in an oven. Remember, this is the only time that we dry something in an oven. We said we don't dry normal crystals in an oven, but you can dry iron nails in an oven. Then we weigh the nails. Now, the one with more increase in mass is the one that has rusted more. Now we need to talk about extraction of metals. So remember that we extract metals from its ore. The ore is the raw form of the metal obtained from the earth. The method of extraction will depend on how reactive the metal is. So if we're trying to extract a metal that is very reactive, more reactive than coke or carbon, then I have to extract it by electrolysis. But for less reactive metals, if a metal is less reactive than carbon, then I can extract it by reduction with carbon. So I put the oxide of the metal with carbon. That is reduction. We don't need to do electrolysis. If we're trying to extract aluminium, now you should know first of all what is the ore of aluminium. The ore of aluminium is bauxite. What is bauxite? It's aluminium oxide with 3 water. So it's hydrated aluminium oxide. The first thing we do is we heat it so we get pure aluminium oxide, which is sometimes referred to as alumina. Now, which method are we going to use for extraction of aluminium? You have to remember, aluminium is more reactive than carbon, so you cannot obtain it by reduction with carbon. So we have to do electrolysis. When we do electrolysis, what is our electrolyte? Remember that aluminium oxide is an ionic compound. It melts at a very high temperature, about 2100 degrees Celsius. So we need to add to it something called cryolite. Why are we adding cryolite? To lower the melting point. So I don't have to heat it to 2100. I can heat it only to 900. Remember, the presence of an impurity causes the melting point to be lower. So the presence of cryolite is to lower the melting point of the aluminium oxide. My electrodes are made of graphite, and I set up the electrolysis. Of course, the aluminium metal is collected at the cathode, and oxygen gas, remember we're doing electrolysis of what? Of aluminium oxide. My electrolyte is aluminium oxide. So I get aluminium at the cathode and oxygen at the anode. But the problem is my anode is made of carbon. So when oxygen gas is formed at the anode, the carbon electrode burns in the oxygen to give carbon dioxide gas. So it is used up and it needs to be replaced from time to time. Remember, the anode in this electrolysis needs to be replaced from time to time. Why? Because the carbon anode burns in the oxygen that is formed. So if he says, name the 2 gases formed at the anode, oxygen and carbon dioxide. When we do extraction of iron, I don't need to do electrolysis. Why? Because iron is less reactive than carbon. So I can extract it by reduction using carbon. Iron is less reactive than carbon, so it can be displaced by it. So we do extraction of iron in a huge blast furnace. Remember, the ore of iron is hematite, and hematite is iron 3 oxide, Fe2O3. Do you remember what was the ore of aluminium? The ore for aluminium was bauxite. The ore of iron is hematite. Now, what happens in the blast furnace? The first thing that happens is we put in, from the top, we put coke and limestone and the hematite. And we pass hot air from down. So if he says what is placed in the blast furnace, coke, limestone, hematite, and air. The first reaction is the coke burns in the oxygen in the air to give carbon dioxide gas. Now this reaction is very exothermic, so it helps to raise the temperature of the furnace. It makes the furnace hot. But then we have a lot of coke, so the carbon dioxide will be reduced by coke to form carbon monoxide, and it is the carbon monoxide that reduces the iron 3 oxide to form iron. So the reducing agent in the blast furnace is carbon monoxide. This is the one that reduces the iron oxide to iron. What is the role of the limestone? Why did we add limestone? Because limestone, which is calcium carbonate, in the heat of the furnace breaks down to give calcium oxide plus carbon dioxide. So remember, this is an example of thermal decomposition. Do you know what's thermal decomposition? When a compound is broken down by heat. So the limestone is broken down by heat to form calcium oxide, which is a base. It will react with the main impurity in the blast furnace. Remember, the hematite is something that we got from the earth. So the main impurity is sand, which we refer to as silicon dioxide. Silicon dioxide is acidic. It's an oxide of a non-metal, so it's acidic. It will react with the base calcium oxide to give what we call calcium silicate, and that is referred to as slag. Remember that this will float in the blast furnace on the top of the iron, so it prevents any reoxidation of the iron. And at the same time, when we remove it from the blast furnace, it is used in rod making. How do we extract copper from a mixture of copper carbonate and impurities? So he's telling me I have something called malachite. Malachite is a mixture of copper carbonate and insoluble impurities, and I want to extract copper. What should we do? The copper carbonate or the malachite is a solid. So the first thing I'm going to do is crush the malachite in mortar and pestle. And then this is a carbonate, so it will dissolve in acid. So we add dilute sulfuric acid, for example, to the solid malachite in a beaker. The copper carbonate solid will dissolve to form a blue solution of copper sulfate. Then any insoluble impurities, we will get rid of it by filtering through filter paper and funnel. Now I have in my filtrate, I have copper sulfate solution. How do I get copper from that? Remember that if I have copper sulfate solution, I can add magnesium powder. The magnesium will displace the copper, so I will get a brown precipitate of copper formed. Filter through filter paper and funnel, I get the copper as a residue. Wash the residue with a few drops of distilled water and dry between filter papers. So we had copper carbonate and insoluble impurities. We added sulfuric acid to dissolve it to form copper sulfate, and we filtered to get rid of the impurities. Now the copper sulfate solution, if I add magnesium to it, the magnesium displaces the copper and I get the copper as a precipitate, get it as a residue when we filter through filter paper and funnel. Following? Okay, this is another question. Sulfur dioxide gas is a common pollutant formed when fossil fuels burn in air. Sulfur dioxide can be detected by using an acidic solution of potassium dichromate. Remember we said sulfur dioxide gas, what is the test for it is we put acidic solution of potassium dichromate. The dichromate changes from orange to green. Or we had a use of potassium manganate, and the potassium manganate changes from purple to color. So here he's telling me I'm going to use potassium dichromate, which is originally orange. And when the sulfur dioxide reacts with it, it turns from orange to green when a certain amount of sulfur dioxide has reacted. Okay, what does he want? Plan an experiment to investigate which of 3 different samples of coal produces most sulfur dioxide. Remember we said sulfur dioxide gas is the gas that causes acid rain. Where do we get it from? We get it from burning fossil fuels that have sulfur impurities. So the coal, if you burn it, it gives sulfur dioxide, and I have 3 samples of coal. I want to know which one gives more sulfur dioxide gas. So what should I do? The sample of coal I can put into an evaporating dish and burn that. Okay? And then collect the gases that come out using an inverted funnel, pass it through potassium dichromate solution, and measure the time taken for what? For the orange color to change to green. And the one that changes color faster will have more sulfur dioxide. Are we following? So weigh 10 grams, for example, of the first sample of coal using balance. Put into an evaporating dish, cover with an inverted funnel connected to a delivery tube. Put 20, a specific amount of potassium dichromate into the test tube using measuring cylinder. Put the delivery tube into the test tube. Burn the coal, measure the time taken for the orange color to change to green, and then repeat using the same mass of the other samples of coal and same volume of fresh samples of potassium dichromate. The one that causes faster change in color produces more sulfur dioxide. This is another experiment. It says fizzy drinks contain carbon dioxide gas dissolved in a liquid. The carbon dioxide gas can be removed from the fizzy drink by heating. So if I heat the fizzy drink, the carbon dioxide gas comes out. Plan an investigation to find the volume of carbon dioxide gas in 1 decimeter cubed of fizzy drink. 1 decimeter cubed is a huge volume. Include in your answer how you will calculate the volume dissolved in 1 decimeter cubed. Now you are provided with only a small sample of the fizzy drink. So you're going to work on the small sample and then calculate for the 1 decimeter cube. Okay, so what should we do? He's saying if I heat the fizzy drink, it gives out carbon dioxide. So measure a specific amount of the drink using a pipette. So I can put 25 centimeter cubed of the drink using a pipette and put into a flask connected to a gas syringe. Then what? Heat the flask until no more increase in volume of gas in the gas syringe. Okay? Determine the highest volume of gas collected. Now, this is the gas collected from what? From 25 centimeter cubed of the drink. He wants the amount of gas in 1000 centimeter cubed. So you're going to multiply this amount of gas by 40 to determine the volume that would be collected from 1000 centimeter cubed. Are you following? Another question, very quickly. Fertilizers are used to increase the growth of plants. Fertilizers have to dissolve in water if they're used by plants. Plan an experiment to find the solubility in gram per 100 centimeter cubed of a certain fertilizer at a certain temperature. So he's giving me fertilizers and I want to know how much will dissolve in 100 centimeter cubed of water at 30 degrees Celsius. So what should we do? Weigh a specific amount of the fertilizer. So we're going to weigh, for example, excess 100 grams of fertilizer using balance. Put into a beaker, add 100 centimeter cubed of water using measuring cylinder, heat to 30 degrees Celsius, stir the solution until no more solid dissolves, and then filter. So you're going to filter whatever did not dissolve. Filter through filter paper and funnel, dry the residue between filter papers, weigh. So this is the mass that did not dissolve. If I subtract it from the original mass, then I can determine the mass of fertilizer that dissolved in the 100 centimeter cubed of water. Are you getting better at that? Okay, another question about fertilizers. He's saying we have 2 types of fertilizers. The fertilizers improve the growth of plants. A farmer decides to buy one of these fertilizers to improve the soil on his land. Plan an investigation to find out which of these fertilizers would be best for the farmer to buy to grow beans on his land. So he wants to know which of these fertilizers is better to grow beans. So what should we do? Obtain 2 bean seedlings. So I'm going to test this on 2 bean seedlings that have the same age, same height, same species. Measure the initial height of each seedling. Put the seedlings into the same amount of soil. Add equal amounts of water. Weigh equal amounts of fertilizers using balance and add 1 to each soil. Leave for what? 5 days at the same temperature, so at room temperature, and we measure the final height of each seedling. The one with the more increase in height is the better fertilizer. How are we doing? Okay. This is the end of this review. Please practice explaining these experiments and remember what we said about the important chapters related to paper 6, and thank you for listening.